Buenas tardes a todos. Gracias por el interés en el curso de Deep Learning y aplicaciones en física y astronomía. Para mí es un placer presentarles a los docentes del curso, colegas muy estimados de Río de Janeiro, el doctor Clécio de Bom. Él es físico, es profesor en el Centro Brasileño de Pesquisas Físicas de Río de Janeiro. Se especializa en las técnicas de Deep Learning aplicadas al campo de la astronomía. Y es miembro de la colaboración SPLAS, así es como yo tomo contacto con él. Es actualmente el spokesman de la colaboración, o sea, es la persona que se encarga de dar difusión sobre los datos que se están teniendo y la ciencia que se está haciendo con SPLAS. Y también es miembro del proyecto LSST y PDF. Así que los dejo con Clécio y espero que disfruten esta parte teórica del curso.
Thank you, and thank you for all for joining us today. It's my pleasure to be here in La Plata. I've been here more than 10 years ago, so it's back to be around here again. Thank you, Analia. Thank you, Luciana, for assisting me during this short course. So it's working. I hope you enjoy, and I hope we learn a little bit together about deep learning. I usually teach these classes in Portuguese and in Brazil, and it should be usually longer than what we are doing here. So I'll make my best to not talk too much, and we keep on track on everything I would like to tell you. Okay, so. I think it's working. So this is the name of the class, right? You are discussing about deep learning applications in physics and astronomy. Is a sort like of continuity of what Laerte Sodré Jr. did last year, but specifically in deep learning. So also an honor to. Oh, I think the microphone is coming over and back. Anyway. So this is a little bit of bibliography, if you like to. Yes, I think it's going to be useful. We're going to switch microphones. Can you all hear me? Yes. Thank you. So some bibliographies here. So a little bit of books where we can discuss this kind of subject and technique. We usually don't have a lot of books written because the area is evolving so fast and things are changing all the time. But this is a little bit of some of books I used to recommend people. One of them, the deep learning book made by Goodfellow et al., which is one of the main reference in the field, is completely online, so you can download it, you can look at the book and see for yourself. So that's one piece of advice. The other piece of advice is we're gonna have a lab here with Luciana and myself in the next in the second part of the class. So after we finish the theoretical introduction, so I recommend strongly that you bring your own laptops so you can see the deep learning in action, right? So that's another good thing. So given this piece of information, I would like to start telling you what are we doing here exactly, which is not always clear for a lot of people, since deep learning and artificial intelligence has been to a hype in these following years. So there's a lot of people talking about it without really understanding what's going on, or at least have some
sort of small information of what we are doing. So I like to make things as clear as possible as a professor. So I'll start making the case so you to understand the aims of our classes, right? So there is a big field called artificial intelligence, which is this blue one, which is mostly dedicated to simulate and emulate and mimetize um, the actions and decision process making or some function that only a human intelligent being would be able to. You know that this horizon has been enlarged in the last couple of years, since animals are capable of doing more things that we would expect. But anyway, artificial intelligence has this sort of boundary, right? So one of the main examples that we have in this field is in the early 90s. Many of you are not even born yet, but there were a lot of algorithms that could play chess, right? And they beat me every time I try. So I get this memory from my childhood. And this is a very common example of what we call artificial intelligence, since we can explicitly use their algorithms to explain the how to work, how to play chess and calculate the next move, right? So this is artificial intelligence, but not exactly machine or deep learning. So that's a good example to start with, so you understand the difference between the fields. The next area, which is inside artificial intelligence, is machine learning. So in machine learning, the thing is different. So the trend is different. We are talking now about algorithms that can learn through data. Okay. So remember that I mentioned that the chess was done. There's a explosion of people playing chess with these algorithms in the early 90s. There was even examples of big companies making challenges between humans and machines that time. But later on, we could make machine learning a more strong field than before because of the availability of data. So machine learning is when you give the algorithm data to learn from it. So you don't explicitly put into an algorithm the rules between, for instance, classification or regression process. You just give data and ask the algorithm to fit in, right? This is machine learning. So this field could only bloom later on when we could have a lot of data in the when you start talking about the big data, okay? Which is more like the 20s, the 21st century. And then deep learning, okay? Deep learning is the more recent stage of artificial intelligence that have blooming more recently, which is related to use of sophisticated algorithms that learn through almost poorly processed data, right? So we use mostly rough data in many cases, but the main trend in deep learning, you are fitting with a huge algorithm. What we're talking about is around 10,000, 100,000, millions, 100 millions, and even billions, right? The most straightforward example is ChatGPT that you probably all heard of. I can't heard anymore because every day someone asks me something about ChatGPT and how they will conquer us, or how ChatGPT will take my job. So, but anyway, is an example that's being spread all over the world, and for the first time, it's easily accessible to people, right? Before, you have machine learning algorithms suggesting what would you like to see, what the next move or next series you like to see. But for the first time with ChatGPT, everyone, pretty much everyone with internet access, can go log in and ask the artificial intelligence what it is. And what are you, which is one of the most common questions people ask to ChatGPT. Okay, so I usually have a big colloquium about ethics and implication of these definitions. So today I'm going to straight to the points because we don't have much time. But roughly speaking, artificial intelligence talks about everything that try to mimetize and give some function to a machine that was previously only the human domain, right? Or at least you need some to be a little bit smart. So machine learning, the algorithm learns from data, and deep learning, the algorithms are getting very sophisticated with thousands or millions or even billions of parameters of it. Okay, so these frontiers are a little bit open. They are not very straightforward. This field has emerging for decades, but now they became important in many applications, right? So into machine learning, which is my next point, you can see the issue mostly in two ways. There are more than two ways. This is not an exhausting list. Okay, so you can see them by talking about supervised learning and unsupervised learning. There are other possibilities like semi-supervising, like reinforcement learning, and so on. But most of the cases we are divided broadly in these two categories. So what are the tasks? So we can do classification, regression, that's the most common task in supervised learning. And there's a lot of different techniques for it. So suppose vector machines, linear regression, decision tree, naive Bayes, neural networks. Many of these techniques you might have seen in the last year course with Laerte, right? The unsupervised part is mostly related to clustering. So you ask the algorithm to find some pattern that's not that you don't teach them to learn from, right? You just give the data and ask algorithm, can you see something in there, right? So the evaluation of unsupervised learning is tricky. It depends on a lot of interpretation. In most of the cases, you can do with a bunch of techniques like k-means, neural networks again, some hierarchical models, and so on. In common with all these techniques is you can see is neural networks, right? When doing with machine learning, there's a lot of different techniques. Like some of them are already written in this slide, right? But you can find a whole zoo of techniques. There are enormous lists and things going on all the time. There's light GBM, for instance. That's a very a technique that's been recently used very often. Beyond SVM and variations of the SVM, and so on. And random forests, for instance. So, but in common we have neural networks. In our classes, we are most focused on the machine learning and deep learning, right? When I mentioned deep learning, I didn't mention to you that that's not only about parameters, but we are mostly talking about neural networks. You see that the neural networks can be used to any of these tasks that I showed you in machine learning, while some of the machine learning algorithms can only be used to a certain specific task, like regression, segmentation, and so on. So the thing is, neural networks are very well adapted, right? And people come to my office once a week with a different deep learning problem, ask me, can you solve this? And they don't even know what they want to solve, right? But they want to be solved by neural networks. So you can see so adapted they are. So first of all, I would like to introduce you the workflow, right? Oh, sorry, I came back. Oops. Let me go. So the thing is, how do you use these techniques? There's a whole life cycle in these techniques, or a workflow if you prefer, in how you're gonna frame your problem before you use the technique. And that's my purpose here. So we mostly have a classifier, or in case of supervised learning, and a truth table where you have nice simulations, real data, and this kind of very known data. where you can pretty much control everything. In the case of simulations, you pass through a pre-processing stage. Okay, this pre-processing stage is usually sometimes is overlooked for many people, especially the people that are beginning in the fields. Pre-processing is very important. Okay, usually it's becoming way common from my colleagues from the industry to hire people only to make pre-processing, because this is critical in many scenarios. You then, in the case of supervised learning, you train and you separate in train into validation. Okay. After this process, the trained data will be used to make the algorithms learn. Okay. And there comes the critical part of machine and especially deep learning, which is the training. Okay. So in the training, you have to define what the algorithm look like. Are you using techniques to artificially increase your data? How much of the stores the training validation groups enter stores the training process? Although only the training and only are used to update and optimize the algorithms. So that's a very important step that sometimes gets a little bit overlooked. So once you have a trained model, doesn't mean that it does work. It's mostly not going to work, okay, to be very honest to you. So you have the training model, you can now ask if the model is good enough or is not good enough. So how do you do this? You evaluate the model. For that purpose, I strongly recommend, not anyone does this, but I strongly recommend to have an independent, a completely independent set that we call tests. Okay, so now we have train, validation, and tests. Use the tests to make the performance evaluation. Use the validation only to see and understand if the training occurs as expected, if the algorithms converged or not. Okay, but then you want to make a performance test. Then you use an independent or as independent as possible test. For instance, if you are working in astronomy, I believe it's the most interest of anyone in this on this class, is you can use, for instance, simulations to make training and validation, and use the real data in a test group. Okay, this is not always easy. Deep learning are very prone to overfit, and this makes that your simulation has to be as close as possible as the reality, with a very few or a very small level of idealization. Otherwise, you're probably going to be in trouble. It's easy to understand if you do linear algebra, right? You have tons of parameters to fit. So the most likely scenario, if you don't take care of what you're doing, is overfitting. So now that we evaluate, I'll tell you later on how is evaluate. Does it make sense? Yes, so you can live with that. And then you extrapolate and you can start your real science, right? So many papers that I've seen recently are about stopping in the evaluation of the model, right? So performing technique. While the good, I mean, I won't say the word good, but the real interesting science comes after it, right? When you use your model to actually get some scientific conclusions. Otherwise, the paper and what you are going to do is pretty much machine learning, not physics or astronomy, right? That's an important point. Many people goes over me, students, PhDs, and so on. They are only focused on the technique, not in the scientific questions. So, but the most likely scenario is no, it's not going to work. So what do? Well, you come from scratch. You have to check out the classified data. You have to check out the training. If your classified, if your truth table is good enough, is representative enough, it has enough information about your problem. If it does contains at all the information about the problem you are trying to find the answer, sometimes it doesn't, right? So and then you evaluate the training. So that's the main thing that happens. it's very common to people interested in the subject, as this is a very widespread topic and in the media all the time. They go to tutorials, right? They go to online tutorials. What the tutorial doesn't teach you in most of the cases is the hard part, which is how do you frame this? Because in the tutorial you have everything under control. You have a problem where you know there is a model to solve the problem. So people have done this before. You have data that is known to be representative enough to solve this problem. That's not true in real life. It's not true in astronomy. In many situations, I have to turn back, collect more data, understand a little bit more the data, right? Because this was an unknown problem, how to deal with. So, not to be so, to have a class not showing beautiful astronomical pictures, at least not that beautiful for the moment, I'll give some background motivation on the physical problems or the astrophysical problems I'm most involved with too. I'll give the seminar later this week to talk about other problems, but I'll give you two examples that that I work with and how it came to be a person a person that does deep learning all the time, right? So one of the motivations is strong lens search. Okay, the strong lens search, strong lensing is a very rare phenomenon, right? So there's a very few lenses around there, with millions, 100 millions of galaxies per lens, depending, of course, of a lot of hypotheses you put. And how do you find them? Strong lenses are rare. Strong lenses give you information about dark matter structures. So that's a very important piece of information to have. Strong lenses can be used to perform time delay cosmography, which is very important to try to solve, or at least to give some light, shed some lights over the Hubble constant tension in cosmology. So I think I made the case why we need strong lensing, right? And they are rare. So there's been a challenge, a data challenge in the astronomical community related to Euclid-like data, where the community was given 100,000 images of strong lenses and non-strong lenses, right? With the bands and the configurations that will be Euclid-like. So we have this data, and there was a community wide open data challenge to do this. So you can see in the bottom of the slide, some of these images. I put only the beautiful lenses, which are easy to spot. But in the practical, in the reality, many of them have few pixels. You don't really find them easily on your eyes. But so to have you so to give you some motivation on how to do this. So one of my most known algorithms is the solution that won this data challenge. Right? It was a very interesting data challenge because the data has different resolution. You have to deal with this problem. The other strong motivation that I think it's more close to the groups around here is galaxy morphology. Okay, so galaxy morphology is a problem per se. So there's a lot of things going on. There's recently been galaxy morphological catalogs from the Legacy survey, or at least to a part of the Legacy survey. I did this in S+, so you can see the S+ data, where I work with Analia, Claudia, Laerte, and many others, and the Legacy survey data. Okay, so the test that we have to solve is try to classify between ellipticals and spirals, or early type, late type galaxies. Okay, to this end, we developed our own algorithms. We customized them to make it work, and what happens is way challenging than, for instance, the Legacy survey if you look through the image, because the resolutions are not as good as the DCAM data, which come from Legacy survey. So it's very challenging. You can see in the top on your left you can see examples of galaxies as they look in S plus and as they look in the legacy survey. For instance, in the first row, the third image is very hard to spot if it's real a spiral or not. In the legacy, that's quite clear, right? So that's what the challenge was given to me, and I decided to tackle it with the help of a lot of people from S plus and also the students that came after it. Okay, so to build a catalog of automated way with deep learning. So, oh, sorry for the slide. I forgot to translate this one. What are we actually talking about when you talk about neural networks, right? Once I give you the final version in PDF, I'll translate this one. Sorry about that. But I think Spanish is close enough, right? So the idea behind neural networks and how do we solve these complicated tasks like classification, like regression. One of the things I do on a daily basis is getting photometric redshifts and classifying astronomical transients. How do we do everything with this? It's a very, very simple and powerful idea. The idea is to represent a neuron in terms of make a mathematical representation of neurons, okay? And so I gave you an example of a schematic neuron on the left side and a mathematical one that we use in machine learning neural networks fields, okay? So the main idea is there's a lot of inputs that I call X, so X0, X1, X2, and we combine them, we make a linear combination over it, and that's inside the neurons. It's this small, this is circle, this big circle in the image. So that's you make a linear combination with the weights Wi. So for each input, for instance, X0, there will be the weight W0, W1, and W2, right? For each of the inputs. So we make a linear combination, which means we multiply per each input its corresponding weight and some a constant that is called bias. Is a free constant not related to any input. Okay, so that's the main idea. This is the mathematical neuron. And how does this relate to the real life neuron, right? So I don't know if you're aware, I'm not a biologist. As I mentioned, I'm a physicist that well try to do astronomy, right? So I'll risk myself talking about biology a little bit. So the idea here in the neuron is that your neurons get stimulated, right? If you see something, for instance, certain neurons you get stimulated with a certain pattern, okay? And this represents the inputs, the stimulus go inside the neuron that receive the response. The response could be in a very easy form of phrasing this. The neuron will fire up, right? So they will turn on. That's the idea. But not every neuron. The neuron related to that specific stimulus. If it's an image, it's if you like cats, for instance, and you think cats are, I don't know, it's if you have strong feelings for cats, it will give you make a stimulus in certain patterns and certain neurons on your brain. Just as a didactic example, it's not exactly like this, and some neurons will fire up. Okay, the same idea holds for neural networks. So you will be stimulated by the inputs. The neurons will weight this stimulus. For instance, if the neurons is related to trying to find round patterns, for instance, it will fire up if you see a tire, for instance, or a circle. Okay, it will not fire up if you see a square. So that's the main point. Okay, so but the powerful idea is that these neurons connect to lots of others. So you can connect to hundreds, thousands, and millions of other neurons. And the great secret is how do you define these weights? Okay, So how exactly you define these weights? There are some theorems that you can prove. It's not hard to prove. It's not my purpose here, but not hard to prove that you can map any Rn function, the real group, into an Rn, right? So make a very wide possibilities of function represented by neural networks. But the same theorem doesn't say anything about how do you define this solution, and that's the problem. We know the solution exists. You can simulate pretty much any kind of function that you need in astronomy. But how do you do this? That's the hard part. That's where the train came along. And just as a matter of comparison, if you the biological neuron that gets simulated, electrically stimulated, right? You have way more connections than the neural network that we usually do. Does this mean that at a certain point I'll have a computer as smart as us? Probably not, right? I cannot prove it, but I have a good evidence that that's not the case, simply because neural networks work in a very different way than the human brain works and the biology works, right? That's important to say. So we have an order of a couple of thousands. This will all times change or more, let's say, connections between our biological neurons than we typically do in neural networks. But of course, I'm talking here today in 2023. This landscape will change shortly after, but still, this doesn't mean that we can simulate the whole human brain inside it. It's just an exploration, a very enlightening inspiration on trying to give a mathematical vision of a neuron. So here, just an example on how this works. So you have this what we call perceptron, which is the simple neuron that I showed you. So first the data gets input and gets weighted. You sum them up, you add a bias, and then you put an activate function. Remember that I mentioned that the neurons fire up and fire down? So the idea of the activation function is pretty much this one. I will combine linearly, and then I'll squeeze into an activating function that will give an idea on how much this neuron gets stimulated by the inputs. Okay. In terms of mathematics, what it's doing is adding non-linearity into the problem. If you only make the linear combination, you get in trouble in several situations that requires non-linearity. Okay. So the thing is, you initiate your algorithm, you make this processing, and how do you define, in fact, the neural network, right? You have to train, and this training is made by optimizing the inputs, okay? Optimizing the weights for the given inputs. That's how it learns from the data, okay? And I'll shortly present how this is done. This is called feed forward and back propagation. This is the main algorithm that people use for this purpose of optimizing the neural network. So in this scheme, you are looking at two inputs, x1 and x2, two neurons that we call h1 and h2. These are known as hidden neurons, okay? And two output neurons, which is called O1 and O2, so O from outputs, okay? You can see that at every connection is related to a weight, so W1, W2, W3, W4. I think I can use a pointer here. This will be useful. So you can see W1 here, W2 here, W3 here, W4, and so on. Okay. So the task is, how do I optimize for to solve a problem. You have the inputs, you have the output that's going on here, and I want to make a connection in the way that the weights map me to the right and desired outputs. Okay, for this task, what we do is the feed forward. So we calculate the answer of a neural network. So let's say you chose H1. Okay, let's look at H1 right now. So as you can see here, H1 is a linear combination of what is going inside this neuron. So X1 and X2 weighted plus the bias, okay, which is the linear, the unrelated to the inputs. Okay, and then you squeeze it into a activation function that will give you the final stimulus inside the neuron, okay, and later on you pass this information to the other two neurons, okay. So next, oh sorry, that came out wrong too. You put the activation function in H2. So this is the same thing for H2, okay. So just look over here and here, linear combination, had a bias, and squeeze into activation function. I'll tell you later how to choose the activating function. Is not a random one, and there is specific meanings for each activation function that you need to use, okay. So you do the same thing for the outputs, but the outputs neural, they receive the information from the previous neurons, okay. In this case only two, so H1 and H2. You see what enters inside output 1 is the already squeezed one inside the activation function, output of neuron 1 or neuron H1 combined with the new weight and so on for the other neuron, okay. And then the final outputs from this neuron that you're going to receive is put inside another activation function, okay. All right, you do the same for the other output, which is output 2, as you can see here. And that's the beauty of it, right? So what you have here is a very simple scheme where you can map some inputs into outputs, and this can work as a generic function in many ways, limited in this case for the name of parameter that you're using, okay. As you scale up the neural networks to many neurons and layers, so this is one layer, this is a neural network with one layer, okay. You end up with way more parameters that you actually need to represent a function, so it's not optimized for it, and what you get is some of these weights you get very low numbers. So that's the idea in how to deal with a lot of parameters, okay. So what you do is you get the outputs, okay. You have the error. So this is the what you got, and this is the real points, the real output you like to. So you can measure the error, okay, and you can define a cost function. A cost function, in this sense here, it can be any function that can be optimized to make the actual output of a neural network to be close to the real one, okay. So this is the real data, the truth table response of expected response compared to the response that you got in your neural network, okay. It can be a chi-square, for instance, but it can be very different and complicated things. So this is a very easy example. So you define what you call cost function, and the job now is what? Is just to optimize your weights to make the cost function, which compares the error you're getting with the output from your network for the real data, to be as low as possible. So that's the main idea. It's an optimization problem, right? If you are in this slide, which is slide 20, and still believe that machines are intelligent by themselves, I think that's the time you really understand that it's nothing at all. It's just a matter of optimization problem. That's what you do here. Okay. So how to minimize the costs? So that's the main question. That's the million-dollar question, right? So how do you do this? You simply, well, for optimization choices, you put a factor here, because if you well remember your calculus class, what you're going to do here is to take the derivative, okay, to make the gradient. So that's the main idea. You take the gradient into respect to what you want to optimize, which is the weights, okay? Now it starts the back propagation part, when you go backwards into a neural network, okay? So how do you start? You have the cost function, okay, and you want to optimize each of the three parameters, which is W1 to W8 here, okay? So let's choose W5. What you're gonna do is take the gradient in relation to W5. So you have the cost function with your total error, okay? And you take the gradient over it using the chain rule, okay? You just take the chain rule until you get to W5 parameter, which is this one, okay? So you make the derivative to the output after the activation function, from the activation function to the output of your neuron, the output of your neuron until the actual weight, okay? So that's the idea. Once you do this, you develop a rule to optimize your parameter. And what is this rule? Well, if you remember your calculus class, what can you do is to optimize a function, to make the costs go to the lowest value, you approach the direction of the gradient. And this is exactly what we do here. So we update the new weight to be the weight that we had before, minus a constant in this case, and the derivative. This is a constant you can control, okay? So you can control how much it will jump towards the direction of the gradient, okay? So remember, your calculus going to that direction will minimize the error function. So that's the main idea, okay? It's a simple and powerful idea, because now you can make this structure as complex as you like to, okay? You can make them very complicated. You don't actually need to connect all neurons to all of them, like we are doing here. Each layer connects to all layers to in the next round. You can make as many layers as you want, limited to your computer or your servers, and you can then represent as many complex functions you have, if you have enough data to fit, which is a big issue, right? That's what we call machine learning, deep learning are data hungry. They need a lot of data to make this fit, right? If the data is representative enough for your problem, okay? So this is one example of this. It's just an illustration of approaching to the direction of the gradient. Okay? Okay, let's go to the loss function, right? I showed you one loss function, but the loss function is it doesn't have to be a chi-square. It can be uh, anything that fits into your problem. Okay. So the idea is that the loss function needs to compare the true and the predictions. So now you're using this term predictions is what the neural network gives to you, the predictions. Okay. So one good example in terms of classification problems is the cross entropy loss, which is represented by this one. Well, if you come back to statistics class, you see that this function here assumes that there's two probability distributions, and it wants to make them as close as possible. The minimum of this function here is when p is equal to k, the two the prediction and the probability of pertaining a class in case of classification, and the probability of being pertaining a class in terms of the predictions, right? So if you are making a classification, you are usually not bounded, but is a common choice, the cross entropy. Okay. So for every task that you have, you define a different loss. So this another one here is a different kind of loss. It's not the chi-square, it's the absolute difference. There are specific losses for segmentation. So for instance, if you are looking to segment a galaxy or to deblend a galaxy, you have specific loss function for this purpose too. Okay. So there are also a choice of algorithms to make this to make everything work, right? The optimization algorithms. How exactly? I showed you a very simple example of backpropagation, but there's several ways of doing this. And again, if you come back to the calculus classes, you see that the way I showed you, I have no guarantee that I will find the minimum. Okay, I can be locked in the relative minimum, for instance. Okay, so there's also lots of different choices. This is just some of them: the stochastic gradient descendant, adaptive gradient, and so on. Many of them will define the speed of convergence in relation on how do you how fast you follow to the in the direction of the gradient, for instance. So there's a lot of different choices. Some of them will be more computationally expensive than others. So this is some of the things. The good news is that I'm give you and empowering you presenting all these concepts. But many of them will be will have default parameters that will work. Okay. So this is what we expect to see during the training process. Okay. So if the training process goes smooth, you have this loss here. Sorry, I put in here, I forgot to put here. You have a loss, is what you're trying to optimize. You have the train and the test, validation. So here, as you can see here, the validation part, you don't use to optimize the algorithm. You use only the train. But you use the validation to see if the result makes sense. If the data not used to train follow the same pattern. Okay? So as you can see here, it does. This is what we typically expect. And what is this axis? This is what we call epochs. Epochs for deep learning training means when you pass all your training data through a network and optimize over it. So let's say I have 10,000 points to make the training. Once I pass 10,000 points, that's an epoch. And then I will restart the process. and that will be the following epoch, and so on. So the optimization is given in several steps that can be as fast as 3 or 4 steps and can be 200 steps. It really depends upon the problem you are trying to frame, the complexity of the problem, the architecture you are trying to use. Okay, so this is an example of good training, and this is what went wrong. I'm not trying to shame my students, but this was done by my students. So and you can see the training going very, very wrong. Okay, what happens? What happened here? Different from here. If you look at the curve, at the training curve, you see that it doesn't fall quickly. It's very, very slow going towards a minimum. Okay, so this already calls up some attention. This might mean the neural network is not complex enough, for instance. So there may be simple. That's one possibility. But the main issue here is not the fact that it goes slow to a minimum, is what happens to the validation. If you look at the validation, what you see here is a mess, right? The loss, which is a measure of error, is getting bigger and bigger along the epochs. This is what we call overfitting. Okay, it does overfits. And if you didn't use the validation, you will be convinced that the neural network is doing a good job, which is actually not doing a good job. This neural network is useless. It cannot be applied to anything. If you apply to a real data, that's what happens. Okay, but it does represent very well the training set. This again is related to the fact that there's just too many parameters to be fit. Okay, how do you mitigate this kind of problems? There are techniques very important that's called dropout. Okay, so a dropout technique where you select neurons time to time and drop them out. Okay, so what's the idea? The idea is to try to prevent overfitting. Okay, if you from time to time you have too many parameters and you start to getting very, very specialized in your training sets, what can you do? If you from time to time just erase or reinitiate some of the neurons during the training process, this will help the neural network to generalize. Okay, not to be too specialized in a certain specific training set. It also will make the neural networks to find different connections to respond to the same desired output. You create paths throughout the neural network. So you give you redundancy. Okay, it will make your. So this is an example of what you could drop out. Okay. Activation functions. There is many of them. The one that I showed you first is the sigmoid. It is a good representation for two reasons. The first one, if you look to sigmoid to statistics, this actually does represent, depending on how you frame the problem, as a probability of pertaining a class. So if you belong to a class, this activation function is closely related to the sigmoid regression technique, and then you can actually use this as a probability. Okay. The other good stuff around here is that it does give you a saturated fired up and fired down results. Okay, the neuron is activated or deactivated. It's continuous, okay, and bounded, right? So the bound the values of your and the thing that goes towards your network is a good idea to avoid what we call explosive gradients, when the gradient assume numbers, very high numbers. Okay. Another common choice is the hyperbolical tangent, which is this one. This one is more computationally expensive. There is some evidence that it might give you a better, more precise results in regression tasks. There is this most popular one, which is the ReLU function that is used to, well, it was first proposed as a replacement of sigmoids in terms of having pretty much the same results with a small advantage for sigmoids, but a very close result, close enough in terms of statistics. So that's one of the good features, but with the advantage of being way more less expensive in terms of computation. And there's also, let's say, our more distant cousins or more distant and weird functions that we can find here. No, my cousins are not weird, okay? It's just it was just a coincidence what I just meant. What I said. So this is the most different ones that you can use. Okay. All right. How to implement everything, because it's time for the lab. The lab time is coming. Okay. How do we implement all of this? So we use many libraries, and there are libraries for everything you want to do. Okay. One of the most popular one is Keras. Keras nowadays is native inside a more low-level library, which is called TensorFlow. In the past, it used also to give support to other libraries. So Keras is a friendly interface where many of these parameters that I just mentioned to you are already in the default mode. Okay? But Keras controls the lower level libraries, right? That are mainly related to the big companies, like PyTorch is related to Meta, and TensorFlow with Google. Okay, as you already noticed it, there is a huge participation of the industry because they see the potential of making money out of deep learning. All right. So there is also other libraries that are related to performance, high performance, okay, and customization, like Flex, which use JAX, okay. But most of the time, if you're not doing something specifically, very specifically, you can live with Keras, okay, or something that demands the complexity of a different library, okay. So most of the time, you use Keras. What I do with my students is use Keras. Keras doesn't work, then you go deeper to, or use PyTorch and so on. Okay, but in many cases, Keras is enough for most of the applications. Okay, the other thing is TensorFlow, which is I just mentioned, which is also very useful library to use on. Is way more customizable. You can customize much better than Keras. Just to give a hint on how this works. So there's a high-level library called TensorFlow. Keras is on top of it. So and this structure, you can program everything in Python, okay? But at some point in the tensor operations, you go to C++, which is way more faster, right? Some people that used to work with computation commonly ask, why do you use Python? Wow, we are using C in disguise. That's what we are doing, okay? And then this go over the hardware. There's these three main hardwares that you use for deep learning, which is, well, CPU, your computer, GPU, the graphic units, and CPU, which is more related to specific for deep learning. GPU is proposed to play video games, right? So people play a lot of video games with GPU. It was used to make a renderization of video game scenarios. So if you are a video game fan, you probably know what GPU is. But as a matter of fact, this kind of operation is pretty much the same operation we need for deep learning. So that's why we use this for deep learning, right? And also, as you might be aware of, some crypto coins also requires the use of GPUs. Because of this kind of operation that is optimized, the tensor operations are optimized inside this. Okay. All right. So, couple of concepts. I already mentioned what the epoch is, okay, which is a forward pass of all training examples. A batch, which is the number of training samples in each optimization. You don't pass all the optimization, all the data, okay, at the same time and optimize for them, okay. You pass 2 batches, okay. These batches can be as small as 1 in critical scenarios, but it usually takes the number of 32, okay. The number of interactions is the number of passes, okay, which you do. That's the other thing. Okay, I'll skip this example. I think I'm gonna directly to the example we prepare for in the Google Collab. Okay, but first of all, I'll introduce one of the issues that we are gonna show in the Collab. So in the Collab, in the lab, I'm gonna show myself and Luciana. I'm gonna show the problem of classification. Okay, classification with neural networks. Today, we're going to use a very simple neural network. And this very simple neural network was historically used in this data set. It was one of the first big success in the 90s of what we could start thinking about calling deep learning, okay? This is a database of handwritten digits. Okay, so what is this means is, well, this. So the problem is the following. If you need to use to send a letter to someone, okay, some people might be too young here to actually send a letter to anyone, but in case you do know what I'm talking about, how can I automatize this? I need to read the postal code automatically, okay? So how do we do this? One of the things could be I can take a picture of the image of the postal code and ask to the computer to let me know what numbers are there, okay? This is also known as CAPTCHA if you are using some sort of security in some system nowadays. And this database, early proposed, has 60,000 images for training and 10,000 images for tests. Okay. So the task is identify what number is, and some of them are really tricky, as you can see here, right? So that's the idea. So now we start our lab with Luciana, and I'll present you the Google Colab. If you have your computer, you can play along, okay? Otherwise, I will present you the code and make a pass through the code. If you have questions, feel free to interrupt me all the time, okay? If you can ask right now before we start the lab, it's up to you. But I'll still be here available all the time. Any questions, comments? While I put...
¿Preguntas?
Okay. I know that the planetarium is a good place to sleep. I'm aware of it. All right.
Bueno, si no hay preguntas, les quiero presentar a Luciana Díaz, que ella va a estar a cargo de la parte práctica. A Luciana la vamos a tener en el YALP un poquito más que Clécio. Clécio lo tenemos con nosotros hasta el jueves. Luciana nos va a acompañar hasta la próxima semana, el jueves 5 de octubre se va. Y Luciana es máster en el Centro Brasileño de Pesquisas Físicas, ahí en Río de Janeiro, y ella se especializa justamente en técnicas de deep learning, pero aplicadas a la industria en general, ya no en el aspecto específicamente científico o de astronomía o física. Así que, bueno, los dejo ahora con Luciana para la parte de la práctica.
I'll stay here just to show the Google Colab. Okay, but you can give the microphone to her. Luciana, please interrupt me at any time, okay? You can interrupt me all the time. But I'll just make a walkthrough. Vou mostrar para ele. Okay, so this is the Google Colab that she prepared to us for today. So if you are not used to it, you received the link earlier, right? So this is pretty much self-explainable. So what the main task that you have to do is to press the play button, okay, all the time, and you go through the end, hopefully, right? I don't guarantee. So this first pass is just to get the data. So this is the first Google lab for this class. And here we're gonna show you, let's go to the next, to the next part. So then you are starting to make, import the libraries, okay? So here you can see the common libraries that we need, NumPy and Pandas, which are using to make operations over data structures, to make plots, matplotlib, Seaborn, also to make pretty plots, AstroPy, that I believe you probably are very acquainted to, and scikit-learn, okay, which is a library for machine learning, TensorFlow that I just mentioned. Okay, we are also importing the MNIST dataset, okay, and some functions that will be useful for us here. So the first pass of the Google Collaborator is to load and present the data, okay? So here we are using data from S+, the spiral galaxies and elliptical galaxies in S+, okay, and also MNIST as an example, okay? So here you're just creating a plot, and you're using Seaborn to make a histogram plot, okay, with these two classes, spiral and elliptical, to see the distribution of spiral and elliptical galaxies. So when you load the data, you loaded the catalog, okay, which is this one. Pandas read this file here, and you're also gonna load the image later on, okay? So here you load the catalog. So the catalog contains the ID, the number of the image, the array and deck, and other informations from S+ database, okay? Like the signal to noise, so on. So if you want to know all the fields, they are here. And this is the plot that we ask, spiral and elliptical, to have an idea on the proportion of these two classes here. Okay? Now the second part is about loading the data, loading the images. Okay? So here you can make this load, feeds get data. This specific line will load each of the image. And here you prepare a figure to show the data as they come. Okay? As I mentioned, one of the issues is that they come without any pre-processing. Okay? This is also some configuration for your plot. And here you are loading the other data set that we're using, the MNIST. Okay, using this function here. So here is the example of one of the images from S+. Okay. Here are the other ones. I hope that in your computer they looks better than in the screen. The next part is what I just mentioned. How you have to divide in 3. For our very with joy, I tell you that there is a very simple function that already does this, called train test split, and we imported this function earlier before in the code. Okay. It's also useful to randomize this data. Okay. So that's one important part. So xtrain, xtest is the inputs, and ytrain and ytest is the outputs. Okay. So you do this with both the MNIST and also the galaxies. Okay. And here you are implementing the model, the actual machine learning model, okay, the neural networks. So you define a model here, there's a function, okay, def model, and here is how the model works. You get some data, for instance, the images we're talking to, you flatten these images. So you actually destroy the spatial information for it, because this is a dense neural network. Okay, as a dense neural network is exactly what I showed you today. Is a network that only contains neurons like the one I showed you that are fully connected to the others in the next layer. Okay, so what you can see here is that you after flattenicize the array, so the array will become the matrix will become an array, and then you put this information into the dense layer. Okay, so here's the dense layer with activation function ReLU that I just showed you. The dense layer contains 256 neurons that receives all this data here. Okay, after this there's a dropout where I lose 10% of the weights. I reinitiate 10% of the weights. Then another dense layer. Okay. Oops, did something that I shouldn't. I think I solved it, right? Yes. Okay. Now with 16 neurons, with activation ReLU again, another dropout. And later on, as is a classification problem, I mentioned to you that we can use the sigmoid function to interpret the result as a probability. Okay. After you define the model, you have to compile the model. Okay, and it's as you can see, by editing these lines here, you define a whole different model. You can put more layers, more neurons, and do whatever you want. Okay. The only important part, at least the most important part, is the output. The output should have the same size of the desired output, okay? So the same shape. In the case of classifying galaxies, you want two numbers, probability of being spiral, probability of being elliptical, for instance. In case of a MNIST, you need 10 numbers, from 0 to 9, to define which class is related to that image. So after the model compile, you define your optimizer, as I mentioned before, lots of options. Adam is a very well used nowadays. You define your loss, which is a kind of cross entropy, okay? And the metrics to evaluate the loss use accuracy. All right. You can print the model you just built with this function model.summary, and then you see what's going on and the number of parameters, the output shape of each of the layers. All right. Here is an also useful piece of information: total number of parameters in your network, number of trainable parameters, and number of non-trainable parameters. In this case, none. Okay. Later on, we start the training. Okay. How do we do this? We define a batch. Remember, the batch is the number of examples in your training set that's being optimized per time. It will optimize to all the data, but you do 16 on each step of the optimization. Then the number of epochs, the maximum number of epochs, and use this function model.fit so you can fit your data. Okay. And here's what you see is the loss going down, the accuracy going up over each of the 20 epochs. Epoch 1 out of 20. The validation loss and the accuracy, the validation accuracy. Okay? If everything goes smooth, the loss and the validation loss will be close. Okay? And it goes up to the epoch 20. Okay? Last but not least, we do a train plot. Okay? Where we are showing here the different situations around here with MNIST and with the S plus example that I just showed you. All right? So you can see that the training in the S plus are not as good because the problem is way more complex than the MNIST. Okay, you also start to see some overfitting in MNIST. This difference around here. Okay, so that's two important things to look after. And I didn't mention today, but there's this performance curve that's called HOC, and last you certainly mentioned to all of you, which is as much as this curve that goes up here and saturates over here, it's close to this corner, it means that's a good classification. So this is the final output in terms of performance. Okay, so you have the class from 0 to 9, representing each of the digits. It gives you a great classification in every case, which means area under the curve around 1. Of course, this is rounded, right? With a harder time with class 9, okay? And this is the result for the galaxies. What I like about these galaxies is that, as you can see, is a terrible result, okay? To show you that I can use the same neural network, it can solve easily a data set that you can find in any tutorial, which is the MNIST. But when you apply the same technique directly into our data that is science data nowadays, like S plus data, you get a very bad result. In the class tomorrow, I'll show how to prevent this, how to make it work. But just to give you a hint how the things are not easy as in tutorials as they look like. Okay? So you can push in the buttons and play with. I already make a walk through it. I can leave you with Luciana that can help you all and can even go to your computers and try to solve any issues you have. Okay? So if you don't have any questions for me, well, thank you, and I hope to see you soon. All right.
Entonces, la idea sería que ahora traten de trabajar sobre el Google Collab que les compartí hoy a través de la página del grupo ALAS y que si tienen consultas sobre la práctica, Luciana los va a ir orientando sobre el procedimiento, las dificultades que ustedes tengan. Y bueno, 4:30, como les comentaba por mail, vamos a tener un café abajo para que puedan interactuar entre ustedes y con los profesores si necesitan.